Okay, I think we are good to go. Another wave particle duality, we have looked at some of the wave properties of matter and the particle properties of matter. I'm still under the particle properties, particle property. Want to look at some of the particles of interest to us in radiology. I did mention some of them later. We'll be looking at electron transition, electron interaction. We'll be looking at positron. We're looking at beta, of course, the same thing with electron. We're looking at neutron interactions, very important for us, especially in nuclear medicine. We'll be looking at um, alpha interaction, so on and so forth. So these are some of, okay, proton is also there, but not too important for us in radiology. We'll be looking at some of these particles and their atomic properties, some of their atomic properties. And from there, we begin to appreciate why they are what they are. For example, in radiobiology, we want to look at this alpha particle having a very high linear energy transfer, very, very damaging to tissue as compared to gamma ray or X-ray. Also want to look at electron, their path, electron having a very, very tortuous path when they are in matter, very, very zigzagging in nature as opposed to alpha, which has an almost linear trajectory. We'll be looking at all these particle properties. But I would like to share one more screen about some of these particle properties, some of these particles and their properties. Let me share this screen with us one more time. I hope we can see that. We can all see that. Hello?
Yes, sir, we can.
Okay, okay. These are some of the particles we have we'll be making use of in radiology. We have alpha particle. Alpha particle has a charge of +2. Alpha particle is actually helium nucleus. Alpha particle is actually helium nucleus for 2. It has 2 protons and 2 neutrons, which gives us a mass number. It has a rest mass of 4.00154. And the rest mass is this AMU, that's atomic mass unit. Atomic mass unit. This one is different from the mass number. Atomic mass unit, the rest mass is different from the mass number. The mass number is just a whole number. This is a mass number A. A mass number. It is a ratio of. Let me not go there. It is just the number of protons and neutrons in an atom, and the rest mass is this. Then the energy equivalent of this is 3.727 mega electron volt. It has a a formula converting rest mass to energy in a mega electron volt. And this energy in mega electron volt can also be converted to energy in a joule, and so on and so forth. The proton here is just the hydrogen nucleus. Of course, we have three types of hydrogen, or rather three isotopes of hydrogen. The normal hydrogen, or should I call it normal? The hydrogen, this other one, and hydrogen 3, tritium. This one has one proton, one electron. This one has one proton. This one has this one's sorry, this is radioactive. So this is actually the proton we are looking at. If you remove the electron in, hydrogen atom, in the normal hydrogen atom, we have a proton. So the proton there is this, which has an elementary charge of +1. And of course, the rest mass is about 1 AMU, atomic mass unit, of course, 938. Then for electron, the electron has a negative charge, and the rest mass is 0. You can see 0.511. Very, very important. This number is very, very important for us in nuclear medicine, especially when we are looking at the rest mass of an electron. So, for example, if one wants to, for us to have in PET, what's the PET, photon. Listen, we have this energy, the energy 0.511 times 2 has to be supplied 1.0 of this 2201. 1.022 mega electron volt of energy has to be supplied for positron, for PET to take place. Why? Because the two electrons, the positron and the electron, they come together. When the positron is traveling, it encounters an electron, and they will be annihilated and give rise to a photon which has this energy, 1.022 mega electron volt. So we appreciate that when we get to positron and electron. So this energy equivalent, it is not just there for us to view it. It's just for us to understand why we have to give this energy, why the photon, why this energy has to be reached for us in PET. Then we have a positron, a positive electron, beta plus. Of course, the energy is 0.51. Then we have a neutron, which has an energy equivalent of 940, very close to that of a proton, slightly heavier than a proton, about the same thing. So these are AMU is just atomic mass unit. We don't need this definition. They found out the 1/12 of the mass of a carbon 12. And this definition was refined from that. Initially, it was based on hydrogen atom, but few years back, this one was defined based on the carbon 12. Carbon 12 is about the most abundant and stable atom. So let's just let me stop the share and continue from where we have stopped. So having said that, I think we go over to the mass energy equivalent. Also very, very important. Mass energy equivalence. These are the key topics, key points we need to know before we go into one of the proper topics in this series, in this lineup of topics. That's interactions of matter, interactions of radiation with matter. That is interactions of photons and so on and so forth with matter. We need to know some of these salient points. We will look at mass energy equivalence. Mass energy equivalence. Mass energy equivalence. And before the time of Albert Einstein, one of the greatest physicists that ever lived. He he proposed a theorem in his special relativity in 1916 or so, there 1912, that because under classical physics, classical mechanics, we often talk of energy being all those things we used to say then. Energy can never be destroyed, blah blah blah. Energy can neither be created or destroyed, but can be changed from one form to the other. But that was discounted, disproved by Albert, that energy can be, I mean, the mass can be destroyed. In fact, when mass is destroyed, it is converted to energy. So he put it in a more compact form, in a much more encompassing form, in a much more broad form, by this mass energy relationship equivalent. That what we have is mass energy, mass energy conservation, not just energy conservation. In a big world, in a classical world, we can say, of course, energy is can be conserved without really leaking. But when we come to the subatomic world, which is actually what we are dealing with in both radiotherapy and radiology and so on and so forth, then we should be, we are always almost talking about mass energy equivalent, because some of the speed of these particles, they approach at the speed of light, or the speed of this wave stuff, they approach at the speed of light. So that is why we have to look at the mass energy relationship, mass energy equivalent. Like what I, like the screen I shared, said the rest mass of electron is 0.511 um, MeV. For positron, it's still the same thing, 0.511 MeV. When you have an electron, a proton, a positron, beta plus, traveling and comes in contact with an electron, they will annihilate, they will disappear, they will no longer exist in what we call, in a term we call destructive production. I mean, destruction. They will destructively combine to give rise to a photon whose energy will be 1.0, the combination of these two. So energy, matter has been converted to energy. So that guy, Einstein, gave this wonderful relationship, which we use every day, both in radiology, radiotherapy, and so on and so forth, especially when we go to what's it called, PET production, which will make use of in PET and nuclear medicine. So we have the relationship as E equal to mc squared. Then as we can convert energy to matter using this, where this m is the mass of whatever we are looking at. So with this, you can actually convert. You can have this. This is the speed of light, approximately 3 times 10 raised to power 8 meters per second. So energy, this mass energy conservation still remains based on this equation. That is, energy can be converted to matter. So this energy, if you have a photon moving with a 1.02 mega electron volt, it can give rise to two particles, which must be electron and positron, negatron and positron, give rise to these two particles, which will now have energies of 0.511 and 0.511. So this one is also very, very important, mass energy equivalence. So having said all this, it's time for us to go into the much more detailed topic in the name of atomic structure. because all these things we have been saying, they are just precursors. They want to prepare us for atomic discussions on atomic structure, because once in a while we'll be looking at all these some of these simple equations. So as they have prepared the ground for us, I think it's high time we move them into the very important topic that tells us so many things about the interactions that go on during imaging in radiology, atomic structure. Atomic structure. Right from our chemistry days and physics days, this topic is not too new. It's not too new. But then we must have learned it as one of the things we had to learn just to move on in life, just to pass the exam. But um, some of us might not know that we come, even if we knew we were coming for radiology. I think maybe a good number of us didn't know. I mean, going to study medicine, maybe a good number of us didn't know that we'll be branching into the field of radiology as some radiologists. So those things we learned there then, they are still tenable today. Atomic structure. What is atomic structure? The topic of atomic structure has gone through so many modifications, right from the rudimentary definition by what's this guy Dalton, atom made up of a nucleus. Even before Dalton, the Plume model definition of atomic structure, an atom made up of combination of blah, positive, this and that, just like that, was just scattered around to make the atom become electrically neutral. Actually, the number of positive charges equals the number of negative charges. But through experiment, especially the experiment carried out by what is this guy Rutherford. Of course, he had two students, Giga and Giga and Max Dean. They performed a groundbreaking experiment, and based on their findings, they saw that this one was no longer tenable. So from there, we have the Rutherford model of atom, which we still use today. An atom is basically made up of a very dense nucleus, very dense and positively charged nucleus. While electrons they orbit round the nucleus at specified energy levels. So the definition is still valid today, but it's been explained. It's been modified by Bohr using quantum mechanical Niels Bohr using quantum mechanical inputs. So today, so many things we know based on this model, that inside this atom we have a nucleus. The nucleus is made up of protons and neutrons. See, whereas we have shells, we have so many shells. We call them shells or energy levels. The electrons here have a particular energy. The electrons here have a particular energy. The electrons here have a particular energy. As they move, as they go further, these ones here are more tightly, they are more tightly bound than the ones here. So if you want to remove electron here, you have to have, of course, the energy you use in removing an electron here is lower than the energy you use in removing an electron here. So we will see why all these things are important, especially when we come to electric when we come to what's it called, photon interactions with matter, with atom, with particle. And I begin to appreciate why characteristic, photoelectric radiation. Sorry, photoelectric emission is different from Compton scattering and so on and so forth. So the nucleus is made up of protons and neutrons, while we have electrons orbiting around, hovering around in a particular, not just it's a two-dimensional diagram, but it's actually a kind of electron cloud moving in a specified orbit in a way which we are not going to go into. We leave that to those studying physics, chemistry, and so on and so forth. But in our basic understanding, in our basic tenets, we will be looking at this electron being given arbitrary letters K, and it has been recognized internationally. And it is the innermost electron is given the shell K, given the name K, this one L, M, and so on and so forth. And the number that can be filled, the number of electrons in a particular shell can't be more than 2n squared. I think the maximum number of electrons that can fill a shell is given by this 2n squared. So for this first shell, the number of electrons is 2 multiplied by 1 squared, which is 2. For the second shell, of course, that is going to give us 8, 2 squared, 24, 8. And for the other one, 2 times 2 raised to power 3, that's 8, 16, and so on and so forth. You're going to have 32, 64, and so on and so forth. But for very big atom, let's say you have an atom that has 48 electrons, it is not just easy. It's not just as simple. 2 will be here, 8 will be here, 16 will be here. There are so many more quantum mechanical input that will make the electronic transfiguration not just very, very simple. We are not going to go into that. We don't need that. Just for us to understand that in whatever any case, this electron, the number of electrons here can never exceed 8. The number here can never exceed 16. The number here, of course, can never exceed 2. Then for the nuclear material, proton and neutron, you also have their shell. You also have their energy levels, of course, shell, similar to the energy level of electron. When we go into, what's it called, radioactivity, we might want to look at that when we come to radioactivity in nuclear medicine. So we are still going to look at the radioactivity here now, but it's going to be a kind of summary we will be talking, we'll be using. Or when you get to nuclear medicine, we go deep into this nucleus, because that is that is a nuclear, that's a nuclear, what's it called, nuclear medicine for us. The origin, the nucleus being our focus. So much as we have electronic binding energy, we also have a nuclear binding energy. So for us to, once if we have a photon traveling, moving in a tissue, of course, tissue composed of proton, composed of so many of these particles and subatomic particles. The particle be the atom, and the subatomic particle be the electron, proton, and the neutron. When the photon is moving, it can interact with orbital electron and give rise to one form of interaction or the other. When an electron is also moving, it can interact with this electron or even move close to the proximity of the nucleus. We are going to look at that during X-ray production. So these things are the electronic structure is very, very instrumental in understanding. The atomic structure is very, very instrumental in understanding the radiation, the interactions that these structures, both the electromagnetic radiation, X-ray and the photon, and the particulate radiation, when they interact with matter. So I'm going to briefly, 9:45, okay, I'm going to briefly look at that. So we want to look at the radiation from electron and transition. This is one of the very, very important um, a particulate interaction we are going to look at. Electronic electronic interaction with a particle with atom. How do electrons when they interact with the orbitals? We're looking at the interaction with this orbital. What happens? Um, when we have radiation from electronic interaction, we have an electron moving. We have an electron of a particular energy moving. I mind us that this thing we have drawn here hasn't been drawn to scale. It's just for us for explanation's sake. The distance here to here, the distance here to here is so enormous that the it's this other one, the distance from here maybe to the mid of this is nothing is nothing compared to the dimension of this nucleus. The dimension of the nucleus is nothing. Sorry, the dimension of the nucleus is nothing compared to the dimension of this from here to here. So the essentially almost more than 90% of the atom is empty space. We have less than 10 minutes to end this. We also have to do that again. But in any case, let's continue. So having said that, we now understand in what's it called, radioactivity, no? In X-ray production, why most time electrons don't interact with the tungsten. And we have they don't interact with the tungsten. Most time they just move away without interacting. They form is 99% inefficient. Electron X-ray production is 99% inefficient. Why? Because most times these electrons they don't interact with this orbital electron or this. They go through the empty space and get embedded somewhere, forming interacting and then giving us heat. But the ones that they do undergo transition, do undergo interaction with either the orbital electron or this actually gives us the characteristic X-ray or the Bremser-Long X-ray, which form a part of which form the X-ray we use in imaging. So if an electron is moving, if an electron is moving and interacts with one of these electrons, I mind us, I think I once said the energy holding this electron to this one, or this electron to this nucleus, and so on and so forth, is the binding energy. The binding energy is the energy that must be supplied to an electron in an orbit to take it away, to ionize it, or to knock it off from that orbit in which it's revolving, and in which it's oscillating. If you don't supply that amount of energy, that electron will remain there and nothing happens. At most, the electron will just absorb the energy and then re-emit the energy. It just absorbs the energy, makes it excited, and it re-emits it in form of. So if we have an electron, an electric electron, it can knock off an electron. If it knocks off the electron, maybe it knocks off this electron, knocks it off. This atom has become, it has become charged. It is no longer neutral. And of course, nature abhors something which is not neutral. Nature abhors that. So because of that, electron from other shells, they have to fall down here to fill up this space. And if this one falls off there, of course, this is a whole matter. Some other electron will also fall up to fill in this space. So for this to happen, when this electron knocks off this and goes away, and this one falls here, this one will only fall here if it has gotten a particular amount of energy, which is the difference between this shell and this shell. If that energy is not supplied, if that energy is not supplied by this incoming electron or photon, nothing happens. And when that happens, what do we have? When that happens, for this thing to become electrically neutral, it has to emit radiation in form of characteristic, in form of, it can be in form of, it can be in form of light. It can be in form of ultraviolet rays. It has to emit electromagnetic radiation in form of light, in form of ultraviolet, or in form of any characteristic X-ray. But our major focus is on characteristic X-ray because these two wouldn't be able to penetrate go through the body, penetrate the body well, and be detected by the detector. So for that, for X-ray, for characteristic X-ray, the energy must be above 100 electron volts for us to have characteristic X-ray. The energy must be up to 100 electron volts. These ones, they also have their functions. For example, in a TLD, a thermoluminescent dosimeter, which we wear in our centers. If we're using a thermoluminescent, this one is based on light emission, thermoluminescent dosimeter. The emission of a light when a particular atom has been heated or has been elevated by means of heat energy. Okay. Okay, so if you have sorry, I put electron. If you have radiation which knocks off electron, the electron that has been knocked off will cause one other electron from outer shells to fill in that gap. And if filling that gap, the excess energy has to be re-emitted in form of electromagnetic rays. And the electromagnetic rays can either be light, can either be ultraviolet, or X-ray, or characteristic X-ray. And this characteristic X-ray is such that the energy has to be up to 100 electron volts. If it's not up to 100 electron volts, then we're just talking about light or ultraviolet. So when that happens, characteristic X-ray is the name is characteristic because it is based on a particular atom. If you have an iodine atom now, the K characteristic, which we call the K shell, will actually tell us the difference between here and here. Will actually tell us that the transition, the wave, the X-ray, the energy of the X-ray is coming from a transition of electron in L shell to M shell for iodine, or so on and so forth. So the characteristic X-ray is so termed, is so coined them in, because it tells us the particular element or the particular atom we are dealing with. Characteristic. It is characteristic. This one is characteristic of iodine. This one is characteristic of tungsten. This one is characteristic of molybdenum, and so on and so forth. So that is why, for something like a mammography, we have the K shell energy. Maybe we are using a particular filter. We are using a particular combination of a filter for imaging. We know the energy of the K shell. If you look at the spectrum, if you look at the energy spectrum, we have the spike, and so on and so forth. At this spike, they tell us in particular that is something, the energy here is maybe 32 kilo electron volt. That will tell us that we are talking about what we actually used was tungsten. Oh, sorry. Oh, uh, well, I think we might need to conclude. But before then, I would like us to log in again. I'd like us to log in again. We have less than just about a minute to go. I'd like us to log in again with the same link. Um, and I don't think we spend much more time before we call it a day and then fix another time for our lecture. Please just do bear with me for now and probably for the next lecture. But much later, we will have a better, we wouldn't be running into this problem of having to log off and come on again. So I want to end this meeting and start again. So in 1 minute time, we can come in again.